Okay, let's talk about quantum computing. Since I don't know about quantum computing much, so we just talk about some definitions of the term and then little simple demo of the how we using the quantum computing for the actual sample. Okay, we talk about what is the quantum computing and then about the relative theory of the quantum physics and then what is quantum bits and then why we using the quantum computer nowadays and little demo. Let's talk about this agenda. First, the quantum computers using the principle of the quantum mechanics. There is the two important phenomena of the quantum physics. So let's talk about little bit about that. Quantum computing is one of the using the principle of the quantum mechanics is employing qubits to the perform complex calculation. And then what's the two important quantum phenomenon is? It's about the quantum superposition and then entanglement. These two phenomena is already proved by experiment of the quantum physics. So one is the superposition is the one particle is have the multiple states before we measure. So in quantum computer use qubits that can exist in multiple states simultaneously. So and then we can use this phenomenon for the quantum computing speedups. And then there is another phenomenon is the entanglement, which is two particles can share their states and then one qubit become correlated to the another, and then the one particle make it their states, and then the other particle is automatically changing to their states, and then this phenomenon is the working for the very long distance and then very short time. And then what is quantum bits? Unlikely classical bits, qubits can exist in multiple states simultaneously, which is I talked about before, superposition, and be entangled, which is you can make the structure of the quantum computer and then with the entanglement, and then this one is to make it your calculation is the faster than classical computers, much more than nowadays. So this will enable the potential for the parallel processing and enhance the computational capabilities of the quantum computer. And then now why quantum computing is important. Before we talk about the quantum computers as much, and then let's see about some timelines of the important event of the quantum computer. The first in 1994 Shor's algorithm, it demonstrates how quantum computers could factor a large number of exponentially faster than best known classical algorithm. This is important because which is the nowadays is the RSL encryption is using the large number of the semi-prime number, which is the two products of the two prime numbers. So if we finding using this short algorithm, we can find the large number of the prime number, which is using for the public key of the nowadays RSA encryption. So which is broke our algorithm, the encryption algorithm for nowadays. But fortunately, we still have the time for the making this very large number of the prime number. We didn't make it any efficient quantum computers for working for this. And then the first qubit is the first working qubits using NMR stage. There's 1998. And then there's the D-Wave, the quantum analyzer, which is the first commercial available quantum analyzer in the 19th. 2016 IBM's Quantum Experience, which is offering online access to small quantum processor, making quantum computing resource accessible to the public, which is we can use it for through the Qiskit. And then 2019, Google's quantum supremacy, which is could perform a specific calculation faster than most advanced classical supercomputers. So this is the big event of the quantum computing for and then for future researchers. And then why is the quantum computing is important? Scientists are researching quantum computers for several computing reasons, which is because the building quantum computers is not small field, which is we have to make the qubit is the qubit with entangled in a superposition. Qubits are very delicate, so they are easily get entangled with their noise surroundings. So, yeah, scientists and engineers are racing against the clock to overcome these challenges. But we're expecting sooner or later we can make the efficient supercomputer structures, and then we can using the algorithm for the boosting our calculation compared with the classical computing. Because of the quantum computing, we're expecting exponential speedups. Quantum computers have the potential to solve certain problems exponentially faster than classical computer. Tasks like factoring large number of the numbers, stimulating quantum systems, and then optimizing complex problems could revolutionize the opening new frontier of computational capabilities. And then we can use this for the cryptography implications. Quantum computers could impact the field of the cryptography's Shor's algorithm. For example, for the could efficient factors large number jeopardizing widely using the encryption methods. This has the prompted research into quantum resistance, cryptographic techniques, and also optimization problems. Quantum computers are well suited for the solving optimization problems, such as route optimization, resource allocation, and scheduling. This could have applications of logistics, finance, various industries where efficient resources utilization is crucial. So, quantum computers can be used for the changing our algorithms and the status of the using computers. But so far, we have to engineer in a technical problem nowadays. But we expect things we can find the way of the we can build efficient quantum computers. And then let's see a little demo of the quantum computers. I talk I talked a little bit and then more about this. So which one is the best demonstration of the quantum computers? As we can see that this timeline, the Shor's algorithm, is one of the iconic algorithm for the current computers. We can using it for the realistic situation. So I open up the Jupyter Notebook with the Anaconda, and then I can say import the Qiskit version of the 0.45 one now currently, and then there's the one classical period finding for the period finding algorithm. By the Shor's algorithm, by the Peter Shor, the Shor's algorithm is composed of the three parts. The first part is turns the factoring problem into period of finding problem using number theory, which can be computed classical computer. The second part is finding period using the quantum Fourier transform, and it's responsible for the quantum speed up for the algorithm. And third part is to use the period found to the calculating factors. So let's see the first part of the we can see that the finding period with the classical way. So with the in the we assume that the n is the semi-prime number, and then with the two prime numbers, the product of the two multiplication of the two prime numbers, and then we can finding this algorithm for the finding period. And then there's you can we can using it for the generation list of the prime numbers less than thousand of the less than thousand, and then let choose the randomly two numbers of the prime number, and then generate the prime numbers. So we can using it, and then you can see that the semi-prime number is n 50,851. And then next, we can see that this one is put into the Shor's algorithm, the classical Shor's algorithm, which is we can using it to the P and Q. Is P is the A to the R over 2 plus 1, and then Q is the A to the power R over 2 minus 1. So we can put it into the our numbers into the Shor's algorithm, and then you can see that the semi-prime numbers can be prime factors like 241 and then 221, 211. And then let's implement into the Shor's algorithm. And then you can actually we can try to the execute the Qiskit libraries, and then there is a Qiskit for the quantum circles, and then quantum register, and then classical register too, and then you can for the visualization, and then for the plot histograms. So the first of all, we can try to make it Shor's algorithm with we can try to make it first part is to construct the construct A to the 1 and mod 15 circuit for the when A is 2, 7, 8, 11, or 13. So we can create the circuit for the mod 15 with A is 2, A is 7, it's 8, 11, and 13. And then the second part, we can build the last of the period of finding for the circuit. So we can find the period of finding with 15, and then we can put this initialize and qubits, and then we can put it like to apply the A is power of 4 with 15, and A is power of the 2 mod 15, and then A is power of the 1 mod 15. And then we can build up the optimize the circuit for the 11 period 15. So there's the quantum circuit here, and then for using the supply for the A power 4, A power 2, and then of the 11 or the 15. So you can see that using the gate for the math of the quantum Shor's algorithm for this, and then controls unitary, and then feed forward for the computers. And then And then let's build the and then circle for the A core 7 and then plus circle and the legend. So you can put this Q is the quantum register with the 5 with the Q and the quantum classic register 5 with the C and the Shor's algorithm you can use quantum circuit with Q and C and then circular models to be above. We make the above and then put the Shor's algorithm and the QC and then when A7. So and then you can see that the draw with the NPL. So you can see that. So the quantum circuit is working. And then now using this CADM simulator for the get that the number of the result of these things with the plot histogram. And then so you can see that the simulator result in here and then count of the Shor's algorithm and then you can see the data like this way. So we can measurement is you can using that. So and then we note that is there's period 4 and then there's the factor of we can using it for that. So by the formula of the Shor's algorithm, the P is going to be is the H 7 and R is 4, so it's going to be 3, and then Q is the A is 7 and R is 4, and the A to the R over 2 minus 1 is going to be like a 50, and then common vector of the with that is 5. So and then now we know of the for 15 that is the factor of this 3 and 5. So this is the simple demonstration of the Shor's algorithm. As I mentioned before, unfortunately, we still cannot make the efficient quantum computer circuit for this quantum algorithm, but we're expecting we can find more and more things like that. And then we can improve for then sooner or later there's efficient quantum circuit for the Shor's algorithm, and then we need to find out there is another way of the encryption for the nowadays. Well, as we can see, there's a lot of the possibilities we can use our algorithm for the quantum computer, but still there is a technical barrier, and then there's a lot of things we need to figure out. So I'm expecting about the future, and I want to study more about the quantum computing later on, and then contribute more about this. Okay, this is my presentation so far. So about the computer architecture class, we can see the large of the classical structure of the inside of the computer CPU and the MIPS CPUs and the RAM and other devices, other components of the computer. But and then we talk about the GPUs and then the more advanced the CPU of the AMD. But frankly speaking, the hardware was not really my strength of the computing. But if we understand the structure of the computer more, and then our program going to be more efficient, and then there is a lot of the improvement of our software powers. So that's why I want to continuously focusing on the structure of the chips and then structure of the computer and then studying more about this. Thank you very much.